Until now we just learned one skill, which is to convert a given problem with my mathematical skills to a sum of functions that are inside the table. Okay? Now let's extend the table a bit. Instead of taking expressions x power n as it is without any alternation, it is just like this. What we have learned is to find the integration of x power n as it is, okay, and not something else. We will just learn a new generalization. We will extend it a bit. We will make the table a bit larger. How? The rule is as follows. It says that for any rule in the table, if we take x that is inside the integration and put some linear form, then use the same rule, but remember to divide by coefficient of x, which is a. Okay? What is meant by that? This is the power function rule, x power n dx, which is x power n plus 1 over n plus 1 plus c. Okay? Now it states that if I take this x and I put any linear expression, for example, if I put 3x minus 2 power 5, for example, this generalization states that I can apply the power function rule on this expression. Why? Because a linear expression took the place of x. If the expression was like this, 3x squared minus 2 all power 5, I can't apply the generalization in this case. Why? What is the difference between these two? This is a linear expression that took the place of x. Okay? That is called a linear expression. But what about this? Is it a linear expression?
No.
No. Whenever I have any power greater than 1, it is not a linear expression.
It's kind of parable. It's kind of parable.
Yes, this is a parabola. Yes, this is a parabola. Any power instead of 1 or 0, that is not a linear expression. Okay?
Okay.
So I can't apply the generalization in this case. I just can apply it in this case, for which a linear expression took the place of x. Now I have a linear bracket, power 5. It states that I can use the same rule. What is the rule? Add 1 to the power. Add 1 to the power, which should be 6. And divide by the new power. That is the statement of the first generalization. But still, there is still one step, which is divide by a. So I need to divide by the coefficient of x, which is 3. So that is the solution of the problem. Okay? So what will I do now is take every expression in the table and put a linear expression instead of x, and I will get a new rule. Okay? So for example, I had 1 over x dx, the expression was ln absolute x. Now I have a rule which is 1 over ax plus b will be ln the denominator, which is ax plus b, but I remember to divide by a, which is the coefficient of x. Why that is generalization of this? Because a linear expression took the place of x. Okay?
Okay.
So if I had, for example, this integration of 1 dx over 3x plus 2, what is the result of this integration? That reminds me, that is a linear expression. Look, that is a linear expression. It took the place of 1 over x. So it reminds me of this rule. What is the result of this rule?
Then.
Yes. So that will be also ln of absolute 3x plus 2. But I divide by
3.
3, yes. I remember to divide by 3. What if I had integration of 5 minus 2x all power 7?
This remind me the.
Yes, it reminds me with this one.
Yeah.
Why? Instead of the x, I have a linear bracket. A linear bracket instead of x. So I just add 1 and divide by. So that will be x minus 5 minus 2x like this.
And then divide by.
And divide by
2 minus 2.
Minus 2, yes. What about this? Just the same the same one as this, but I write it 3x plus 2, but all squared.
That's with ln by divided by 3. Okay.
Would it be ln? No.
No, this one is not ln.
Yes, that is not. I can say that this is a quadratic expression that took the place of x in this rule. This is not a linear expression that took x in this rule. But it reminds me with another expression, which is this one.
And then s of x.
Yes, x. That is x power minus 2. I can integrate this. So I can write this as integration of 3x plus 2 all power negative 2 like this. And I can apply the rule of
the first rule.
Yes, it will be 3x plus 2 power minus 1 over minus 1, and I divide by 3. So I am skilled to detect this, a linear bracket, power some number. That power could be positive, negative, could be fraction. I just apply the same rule as long as what is inside the bracket is linear.
Okay.
As long as what is inside the bracket is linear, I apply the power function rule. Okay, I detect that. And in the case that the power is negative 1, I use the ln rule. That is the only exception for this, which was that problem. That is power 1 or it is power negative 1, which will give me the ln rule. Okay? So that happens for any rule inside the table. For example, I learned the rule that e power x is e power x. Now if I say integration of e power 2 minus 3x, that is a linear bracket that took the place of x in the original rule. So I just apply the same rule. It is as it is, but I divide by
3 minus 3.
Minus 3. Yes. If that instead of e it was 5, for example, what will change here?
It's worth 5. Can I? In that case, it's 5 to minus 3. 2 minus 3 divided by minus 3. Like this.
No, remember the original rule. What was it? E power x dx. That was e power x, but I divided by ln, not ln x, but ln
a.
The number, yes, the ln a, which is here in this case it will be ln
5.
Not, yes, it will be ln 5 instead of this. So that's the result. So what will be different here? You will just divide by ln 5.
Okay.
Okay. If I had it like this, integration of 1 over 3 power 5x minus 2. What about this expression?
What is expression?
Should I use ln, for example?
Is kind of a excellent. No, you don't need to use.
Yes, we don't use ln. It is completely different case.
Yeah.
Ln is 1 over a linear bracket. That is not the case. That is an exponential case. But I just, for any exponential, for any form of exponential, we need to put it in this form: a power x or a power a linear bracket.
Okay.
This is 1 over an exponential function, but I learned from my mathematical skills, I can write it like this: 3 power minus 5x plus 2. So that's the same problem, but this is exactly the form in the table. Number power a linear bracket. That's a linear bracket. Okay? So I'll just apply the rule, which would be 3 minus 5x plus 2 over ln 3 and over also minus 5. What if the expression was integration of 3 5x minus 2 squared? Or let's make it squared here. Could I apply the exponential rule here? In this case? No. Because this is not a linear bracket.
Yeah.
This is not a linear bracket. I have a rule, and replacing x with a linear bracket, just in this case that I can apply the rule as it is. We'll learn how to deal how to deal with the problem if I had, instead of x, I had some other expression. There will be something that is called the condition to manage to solve the problem. Okay, but until now we're just learning this skill, that any rule in the table, replace x with just the linear expression, a linear expression. Okay, now if I said, for example, integration of sine 3x plus 2.
In that case, you can do.
Yes, that is, it reminds me with that rule, which is minus cosine x, but instead of x we have a linear bracket. So I can apply the rule, which will be minus cosine 3x plus 2, but I divide it by 3. And so for any, for example, if I had integration of sec squared 3x, I know a rule, which is sec squared x gives me 10x.
In that case,
instead of x we have 3x. Is this a linear expression?
Yeah.
Yes, it is a linear expression, so I can apply the rule. So I can say that it is then 3x divided by 3. Okay? What about this expression? One over root 1 minus something, or bracket, linear bracket squared. This reminds me with integration of root 1 minus x squared. That was sine inverse x. Another rule, we have two important rules. Remember those two. Okay. This rule 1 over x squared, the x, that is these are two very important rules, these two rules. One with the root, which gives me sine inverse, one without the root, which gives me tan inverse. Okay. Now this reminds me with this one. But what is taking the place of x? It is a linear bracket. So, okay, it's okay to use the rule, which will be sine inverse a x plus b, like this.
Okay.
But I remember to divide by a, which is the coefficient of x. Okay?
Okay.
What if I had this? Integration of dx over 1 plus 3 minus 5x all squared.
This one is
tan inverse, yes. It reminds me with this rule 1 plus x squared. It gives me tan inverse x. But instead of x, what is taking the place of x is that linear bracket. So I will just apply the rule tan inverse 3 minus 5x, but I remember to divide by minus 5, yes. Now, what if I made it like this? Integration of dx over 4 plus x squared. This is somewhat tricky.
Yeah, because it's not 1.
Yes, because it's not 1. Dx, I know this rule. 1 plus x, it is tan inverse x. But this is not 1.
Can we manage to divide over 4 and...
Yes, that's exactly what we'll do. We'll take that 4 as a common factor out. So that will be 1 plus x squared over 4.
Okay.
And we can write this as 1 plus x over 2 all squared.
Okay.
Now this expression is exactly that one. 1 plus, but instead of x, what is taking the place of x here? X over 2. Is this a linear expression?
Yes.
Yes. So I can apply the rule. So that will be 1 over 4 tan inverse x over 2.
But instead of divided, we're going to multiply.
Yes, divide by half or multiply by 2.
Okay.
Okay? So that would be like this.
Okay.
Okay? If you just open the light. As we will see that expression many times, we will extend the table. Instead of memorizing these two expressions, which is dx over root 1 minus x squared, or the other rule, which is which is 1 plus x squared, instead of these two expressions in the table, we will find the result of these two integrations, a squared minus x squared and integration of dx over a squared plus x squared. Okay, this one,
I didn't get you.
yes, that was exactly that we have did here.
Yeah.
We took that value outside as a common factor, then we managed to solve the problem. Okay.
Okay.
We'll just do that here, and we'll do that here also. We'll take a squared outside the square root and so on. We'll get an expression for this, will be 1 over a tan inverse x over a plus c.
Okay.
We'll also get an expression for this, will be sine inverse x over a. And we will memorize these two instead of these two.
Okay.
Okay? So, that because we will find these two, or we will confront these two expressions many times as we go on in the course. Okay?
Okay.
So instead of memorizing this and every time we make all these steps and so on. No, we will just memorize these expressions. Okay? And these expressions apply also for, if I had here that was plus, I will just make that hyperbolic, tangent. And if I made that negative, that will be tangent inverse. Okay? So that is the rule, and we add the other rule, which is dx over x squared minus a squared. That will be cosine inverse x over a. Okay? So these are the new inverse rules instead of the previously memorized one.
Okay.
Okay? These are the new inverse rules that we will treat. So what if I had dx over 9 minus x squared? Or let's check before, let's check this. Root 5 minus x squared.
This one remind us with like this.
Yes, we can solve it like this, but now we just memorize the rule. That's the rule. We apply the rule as it is.
Okay.
In just one step.
In one step.
Yes.
Sine.
I just need to determine what is a. This is a squared.
A is 1 and.
So a is, no, a squared is 5. A squared is 5. So a is root 5. Okay? So what is the result of this integration? It will be just sine inverse x over root 5. Just in one step.
Directly.
Okay?
Okay.
If I had this integration of dx over 9 plus x squared, what will be the result? Remember the table, it was a squared plus x squared, it was tan inverse 1 over 8 tan inverse x over 8. That is 9.
In the case, it's going to be tan inverse x over.
Yes, what is a here?
A is 9.
No, that is a squared.
3.
So a is 3. A is always the square root of that number, that taking the place of 1.
Okay.
Okay? So that the rule is 1 over a tan inverse x over a. So 1 over 3 tan inverse x over 3. Just in one step.
Okay.
Okay? What if I integration dx x squared minus 5?
In that case, it's going to be tangent.
Yes, that is tangent inverse. But remember, tangent inverse
square root of 5.
5. Yes, a is square root of 5. But remember that in the rule of tangent inverse, the number was first. Okay? Whenever we have written the rule of tangent inverse, it is expressed like this. A squared minus x squared is 1 over a tangent inverse x over a. Okay?
Yeah.
The number was first. The number was first before the x. Okay? So if I had this case,
we have to put minus.
Yes, we have to put a minus. Then we make it like this. 5 minus x squared. Then, now it is, we can say that this is 1 over root 5 tangent inverse x over root 5.
Okay.
Okay? What about this expression? dx over 5 plus 3x squared. Now this, if it was like this, if it was 5 plus x squared, that I would apply the same rule. Okay? But now it is 3x squared.
Maybe we have to get rid of 3 and then.
Yes, that's one method to deal with this problem. Take the 3 out. We may find, we may take the 3 as a common factor. It will be 5 over 3 plus x squared. What will be a in this case? That is a squared, so a will be
square root of 5.
Square root of 5 over 3. Yes. And that in this case it will be 1 over 3, 1 over a, which is 1 over 5 root 5 over 3, tan inverse x over a, which is 5 over 3.
Okay.
That is one method to deal with this type of problem. Another method, and that is, it is usually done by this method. Another method, which is also correct, but some students forget a step in this new method. What is this method? I just look at it as 5 plus, look at it as something squared. What is the squared in this case?
Square root of 3.
Yes, square root of 3x. Now, is this a linear expression or not?
It is.
Yes, it is a linear expression. So I have the rule of this, but instead of x, what is taking the place of x? It is a linear expression. So I can use the same rule, which is 1 over root 5 tan inverse root 3x over root 5, but I remember to divide by root 3. And many students forget to divide by root 3 in this case. And that's why I recommend to use this method instead of this.
Okay.
But you may know both methods. Okay?
Okay.
So that is applied for any expression like this, dx over 5 plus 3x squared, for example. Integration of dx of root of 2x minus 1 all squared plus 7, and so on. All of these I can deal with these. How? By just as we
did before.
Yes, as we have told you, I know there is a linear expression taking the place of x, and we know the rule for a. Now I memorize the rules with a instead of 1. So that is not considered a problem for now. It is not considered a problem. If I have a number instead of 1, it is not considered a problem for me. Because now I memorize the rule with a instead of 1. I just need to check what is a in this case and apply the rule. But if I have any expression, linear expression taking the place of x, I just remember to divide by the coefficient of x, or I can get rid of that constant or so, or any, if so I can apply it. Okay?
Okay.
The last part in this lecture, we will check some forms which are called quadratic forms. Quadratic forms are like these: dx over quadratic, or integration dx over root quadratic. Okay? For example, if I had something like this, dx over root x squared minus 4x plus 5. If this expression was integration of root x plus x squared plus 5, then I know the rule for this. But now I have a first degree term. This term is annoying for me. It is not exactly the same form that I have learned in the table. So how should I deal with this form? This is called a quadratic form. We deal with it by completing square. Do you know completing square?
You put it in the way that is going to cancel with
You put it in the form of a bracket square.
yeah.
Okay? This is the rule of completing square. If I had x squared plus or minus ax. and assuming that the coefficient of x squared is 1. Okay, what is the rule? The rule is take this x and the same sign, take half of the coefficient of x, which is a over 2, all squared. Okay, minus, this is always minus whatever was the sign here, it is always minus squaring that term. Okay, let's apply the rule in this case. This is integral of dx over root. Now, where should I apply the completed square rule for this expression?
Down inside.
Yes, inside the root. So that will be x with the same sign, half of the coefficient, which is 2, all squared, minus squaring of this number, which is 4. Then I write the remaining number as it is. Okay? So that expression will be integration of dx over root x minus 2 all squared plus 1. This expression is just an expression that I've learned before, but a linear bracket is taking the place of x. That will be the expression for sine. That is sine inverse x minus 1, x minus 2 over 1. Okay? What if I had any number instead of 1 as a coefficient of x squared?
It's going to be here?
No, we take it outside. We just take it as a common factor. Yes, take it as a common factor and deal with this expression as it is. Okay? For example, if I had this expression, dx over root 2x squared minus 4x plus 6. I just noticed here that I have a quadratic form. A quadratic form with a linear term, a first degree term. That reminds me with completing square. If I didn't have this term, it will be easily solved by the original rule. Okay, but because I have this term, so we need to apply the completing square to get rid of this first degree term. Okay, but I have here 2. I can get rid of this 2. I can take it out. That will be 1 over root 2 integration of dx over root x squared minus 2x plus 3. I just have taken 2 as a common factor, then I took it out the root like this.
Okay.
Now I am ready to apply the completing square on this expression.
Okay. And then in the case it's going to be...
Okay, apply it.
Minus 1 plus 3 square. It's going to be like this. It's going to be...
Yes, minus 1. Yes, you are correct.
2 plus 2.
Yes. So that will be x minus 1 all squared minus 1 plus 3, which that will be plus 2. So the problem will be 1 over root 2 dx over root x minus 1 all squared plus 2, which is sine inverse. That is the rule of sine inverse x minus 1 over root 2. A, that is a squared, is equal to, so a is equal to root 2.
Okay.
Okay, so that's the rule of sine inverse. Now if I had this expression,
is there something?
yes, But now I can take the negative outside the root. Now look, the coefficient of x squared is not 1, it is negative 1.
But we can multiply by minus 1.
Yes, but minus 1, but inside the root.
Inside the root.
Okay? Or another way is to take it outside and make the complete square outside, then return it. Look what I will do here. I will take this expression with a negative sign. I will take it x squared plus 2x minus 5. I took that expression outside as a draft. This is a draft. I took that expression only outside but with a negative sign. Okay? Then I will make complete square, my complete square. That will be x plus 1 all squared minus 1 minus 5. So that will be x plus 1 all squared minus 6. Okay?
Okay.
Now I return it again with a negative again. So that will be integration of dx over root 6 minus x plus 1 whole squared.
Okay.
I return it, but I just changed the signs of each term.
Okay.
So that's the problem here, and now that is just, it reminds me with dx over a squared root a squared minus x squared, but what is taking place of x? It is a linear bracket x plus 1.
Okay.
Okay, so that will be sine inverse, that is sine inverse x over a. That is sine inverse x plus 1 over root 6. Okay. Last problem. If I had integration of dx x plus 1. Further in the syllabus we will learn another method to solve this problem, but let's solve it with the skills that we have learned until now, all so far.
If you use
this is a quadratic term.
Yeah.
Yes, this is just dx over x squared plus x. This is quadratic.
And then it's because.
And we have learned how to deal with integration of 1 over root quadratic or integration of 1 over quadratic. How? By completing square to get rid of the first degree term. So I'll just apply complete square for this expression. That will be dx over x plus half all squared minus 1 over 4, and there is no other number here, so I'll just leave it like this.
Okay.
That reminds me with which expression? Tan inverse or tangent inverse or sine inverse or sine inverse? This expression is not a root. With not a root, it is either tan inverse or tangent inverse.
Tangent.
Yes, it is tangent inverse. But what is the condition of tangent inverse? The number must be first. So I just put a negative sign. So that will be 1 over 4 x plus half all squared like this. Now I can apply the rule of tangent inverse, which will be the negative as it is. That will be 1 over a. What is a in this case? This is a squared. So a will be
root square of
the square root of 1 over 4, which is half. Okay, so 1 over half tangent inverse x over x plus half over a, which is half also.
That's it.
Okay, so plus. Okay, so I've learned today the skills of dealing with expressions to make it as sum of functions inside the table, and we learned also the first generalization to that if a linear bracket is taking the place of x. Okay, in the next lecture we'll learn the second generalization, for which when any expression is not necessarily a linear expression. What if I put a quadratic expression, any other expression instead of x? How would I deal with it? That we learned in the next lecture. Okay?
Okay.